So we're going to continue today and talk about some more rotational dynamics. In particular, today we're going to learn about angular momentum. Now, earlier in the course, you know that we talked about momentum, and momentum was defined as P, and it was equal to the mass of the object times the velocity of the object. It was a vector, and the direction of P was the same as the direction of V, the velocity. In rotating systems, rotating objects have momentum as well, and this type of momentum is called angular momentum. Angular momentum. Angular momentum is equal to, of course, everywhere before we saw an m, we've been putting an I for rotational inertia, and everywhere we saw a v before, we've been putting an omega for angular velocity. So the angular momentum, which we actually use a capital L for, angular momentum is equal to rotational inertia times angular velocity, or rotational velocity. Now, if you remember back when we talked about angular velocity, I mentioned it does have a vector nature, and the vector nature is such that it obeys the right-hand rule. So if something were spinning in a counterclockwise direction, for example, then using our right hand and pointing our fingers the direction of the spin, the angular velocity vector would point the direction of our thumb. And so if you can imagine, what I'm trying to draw here is kind of like a three-dimensional picture, right? So this is kind of like a surface here, and if the object is spinning, in a counterclockwise direction as viewed from above, then the angular velocity vector points straight up towards us as viewed from above, or the direction our thumb would point on our right hand if we point our fingers in the direction of the spinning. Okay, so angular velocity does have a direction, and guess what? The direction of the angular momentum vector is the same as the direction of the angular velocity vector, just like the direction of the momentum vector is the same as the direction of the velocity vector. So once again, we continue this direct correlation, if you will, with our new angular quantity, angular variables, with our old rules. It's just now we have this type of momentum because it's in a circle in a rotating system is called angular momentum. And likewise, we had the law of conservation of linear momentum, right? So that when things collided, we could conserve momentum along each dimension. And what we were conserving was linear momentum. Things were moving side to side, up and down, in and out. Now we're talking about things spinning, and so an object will maintain its angular momentum unless acted upon by a net torque. Okay, if you remember, our law of conservation of linear momentum says we'll maintain our linear momentum if the system is not acted upon by a net force. Well, everywhere we saw a force before, we've now been putting a torque. Right? And so the rule becomes here for conservation of angular momentum that if there's no net torque on the system, then the angular momentum in the system will remain constant. So I initial in the system times omega initial has to be equal to I final times omega final. That means if we have an object spinning and something changes in its rotational inertia, then the angular velocity will adjust. So that the same, if this goes up, this would go down. Okay, in other words, if the system starts with this much angular momentum in it, and something happens to increase our rotational inertia, then omega is going to have to drop. On the other hand, if the rotational inertia goes down, then omega would go up, because the multiplication of I times omega has to remain constant, has to be the same number. Here we see a man sitting on a rotating stool with weights in his hands held out. The weights are there just to exaggerate this change in angular or change in rotational inertia. So he has his arms out, so he has a fairly large rotational inertia right now. What will happen if he pulls his arms and the weight's closer to his body now? Well, if he pulls the weights closer to his body, he has going to be lowering and decreasing his rotational inertia, which, as you can tell, increases his angular velocity. Okay, so when he pulls the weights in, he spins faster. And of course, vice versa. If he was going fast and then stuck his arms out, he would slow down. This is conservation of angular momentum. So let's start to get a few numbers involved and look at this, this concept of conservation of angular momentum. Here it says we have a man holding dumbbells out away from his body such that he has a moment of inertia, or rotational inertia, of 100 kilogram meters squared. He's spinning at a rate of 2 radians per second. He then pulls the dumbbells inward close to his body, causing his rotational inertia to drop to 60 kilogram meters squared. How fast will he be spinning now? Well, again, keep in mind, angular momentum has to be conserved. So whatever his initial rotational inertia was times his original angular velocity, that has to be equal to his final angular or rotational inertia times his final angular velocity. In other words, they use sizes for these variables to kind of explain what's happening. At the beginning, he has a fairly large fairly large rotational inertia, and a fairly small, let's say, angular velocity. But when he reduces his rotational inertia by pulling the weights in, then in order for these things to multiply and give the same answer, omega will naturally have to increase. So he will start spinning faster. He doesn't have to use his feet or anything like that. It will naturally happen because of this law of conservation of angular momentum. So finishing up the problem, obeying the law of conservation of angular momentum, okay, L final has to be equal to L original. And so as we said, the final rotational inertia here times the final angular velocity, omega final, those multiplied together have to be equal to the original rotational inertia times the original angular velocity. In other words, I final omega final has to equal I original omega original. So when we go ahead and plug this in, his final angular or rotational inertia was 60. We don't know. We're looking for omega final. We want to know how fast he's spinning at the end. His initial rotational inertia was 100. His initial angular velocity was 2 radians per second. Doing the math on this, we find out that at the end of the problem, the professor here, or the man that's holding these dumbbells, will now be spinning at 3.33 radians per second. So indeed, by decreasing his rotational inertia, his angular velocity increases. Okay, so here we see an animation of a figure skater, and currently she has a moment of inertia or rotational inertia of I0. Okay, recall that rotational inertia is a description of how hard it is for something to turn. If we increase her rotational inertia by having her put her arms out, this will make it harder for her to turn. And so to conserve angular momentum, because the rotational inertia has gotten larger, the omega value, or angular velocity, has gotten smaller, so that the multiplication of rotational inertia times angular velocity remains the same. So when she has less rotational inertia, she has more angular velocity. If we have her pull her arms in all the way to reduce her rotational inertia as small as possible, we see that her angular velocity gets much larger. So this spinning motion that we see from figure skaters as they change the positions of their arms and legs on their body is a consequence of the law of conservation of momentum. So we see that in a lot of sports like figure skating, think about people diving from the high diving board, and doing spins and so forth, people going over the high jump, anything where people have to, athletic events where they maneuver their body, like gymnastics as well. By changing the shape of the person's body, they can change their rotational inertia, which will affect how quickly they spin. Okay, so that's something that's common throughout sports. Now, let's get a little more interesting, and let's think about this situation. What if something was spinning? What if I got on a turntable? Okay, suppose I could stand or sit on a turntable, and I got on it with a spinning bicycle wheel. so that as viewed from above, the bicycle wheel was spinning, let's say, counterclockwise. Okay, and so this is kind of what I show here is kind of like an overhead view. So here's my head right here, and my nose is right here, and my ears here. So hopefully you kind of visualize looking overhead. My hair is much thinner these days, but there I am with my overhead view of me standing there. And let's suppose I'm holding a bicycle wheel that's spinning counterclockwise as shown, and let's suppose it's got 10 units of angular momentum in that direction. Recall that using the right-hand rule, the angular momentum here would be pointing up towards us, okay, the same direction as the angular velocity. And so that's considered a positive angular momentum. So here I would have L equal to positive 10. Okay. The question is, what will happen now if I flip the bicycle wheel over? And I at the same time, I'm kind of standing on a rotating stand here that can spin. So I'm almost like the ice skater. What will happen? Well, when I spin the bicycle wheel over, if you're on the ball here, you realize that when the bicycle wheel's turned over, it will now be spinning in a clockwise direction. Okay, so the bicycle wheel here, okay, is going to be spinning in the clockwise direction now with 10 units of angular momentum. And so the angular momentum of the bicycle wheel is now minus 10. Okay, using our right-hand rule, the angular momentum of the bicycle wheel would be pointing into the screen. And so at this point, we've basically gone from positive 10 to minus 10. Well, nature's not going to allow that. If I'm standing on a slippery surface or a rotating stand, what's going to happen is nature's going to say, no, 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 we had positive 10 units of angular momentum in the system, so we need to maintain that. And so what nature's going to do is take me and the wheel and spin me and the wheel around in a counterclockwise direction, such that the wheel and I spinning in the counterclockwise direction have positive 20 units of angular momentum, so as when that is added to the clockwise or negative angular momentum of the bicycle wheel, I still have a net of positive 10 units of angular momentum in the system. The total angular momentum in the system has to be conserved, not just in the number, but the magnitude, for example, but also the direction. There was originally counterclockwise momentum. There needs to maintain an overall counterclockwise angular momentum in the system. And so this is a fascinating thing to see if you've never seen it, and it's a consequence, again, of this conservation of angular momentum. Here is a video clip of just that situation. The man is sitting on the rotating chair with the wheel initially rotating counterclockwise. When he turns it over, you'll notice that from above, it's now spinning clockwise. But notice what direction he and the wheel start to spin together. They start to spin counterclockwise. He did not push himself. If you notice, his feet are resting off of the floor on the rotating chair. So he begins to turn with the wheel in a counterclockwise direction because we have flipped the wheel over, trying to trick nature. Nature says, no, we had counterclockwise angular momentum in the system, and when you've turned that over, we now have clockwise angular momentum on the wheel, so nature spins the wheel and the person together counterclockwise with enough angular momentum to not only overcome what was, to keep the net quantity of angular momentum in the system the same. Now here we're revisiting the idea of torque, because when we talked about torque before, we looked at it from a very practical standpoint and did not get very mathematical with it. Torque is a vector, however. Torque is a vector, and it follows, again, a right-hand type rule. It turns out one of the ways we can write torque is as shown in this highlighted or equation boxed in yellow. Okay, here. Torque can be written as the cross product of r, the position vector, or the vector that points from the rotational axis, let's say, out to where the force is being applied. Okay, that r is kind of like somewhat like our moment arm, but again, it points out to where the force is being applied. And if we take r and we cross it into F, that gives us the amount of torque that we have. Okay, if you remember, the cross product is going to depend on the angle between the direction of the force and the direction of the position vector, but r crossed into f is going to give us our torque quantity and direction. And so if you remember the cross product, you get an answer that's perpendicular to both of the vectors that you cross together. So if r and f form a plane, then the torque is going to point such that r crossed into f points up the z-axis here as shown, and that would be the direction of the torque vector. So again, the equation that we talked about for calculating torque, looking at r times sine theta being the moment arm, that's still valid. I mean, it's just what we're doing here is trying to show that there's also a vector nature to all this, and that the cross product of r crossed with f, position vector crossed into the force vector, would give you the torque vector. And while we're being mathematical, it's worth taking time to point out that the angular momentum vector, which they've shown as a small l here, okay, that's not uncommon when we get into maybe chemistry or quantum physics. Instead of using a capital L, many times we'll use a small l, but it's the same thing, it's angular momentum. And so the angular momentum vector here can also be written as r crossed into the momentum vector. Okay, or since the momentum vector is m times v, the m being a scalar, it could be pulled out in front, and we could also write this as m times the quantity of r crossed v. So the direction of the angular momentum vector is determined by r cross v here, and of course m is a scaling factor being a mass. All right, so that's one way we can write that. So in other words, if you look at the diagrams here, this one especially, okay, if you take the momentum vector here and you extend it both directions kind of to infinity, almost like we did with torque when we created our line of action, then r perpendicular is the shortest distance from the pivot location or the center of the coordinate system, for example, you know, where you're choosing for the center of your system of rotation, that shortest distance there, r perpendicular to the momentum, the line of the momentum action, that would allow you to then write the size of the angular momentum as r perpendicular times that momentum, or in other words, r perpendicular times mv. So many times you'll see if v is perpendicular to a radius of some sort, you'll see mrv being used for angular momentum. And so that's a common way to relate the angular quantity back to the linear quantities of velocity and mass. Continuing with our theme that for every relationship or every equation we had earlier in the course, we could rewrite it for angular or rotational systems. We talked about Newton's second law was originally written by Isaac Newton as the force is equal to the time rate of change of the momentum, right? F equals dp dt. And we've talked about that numerous times, and we've talked about that in relationship to rocket motion. We've talked about that in terms of a derivation of F equals ma if you have a constant mass, and so forth. If we strictly follow our rules here, in place of F, we would be putting a torque, and in place of momentum, we now put an angular momentum. And so our equation here for Newton's second law in angular form can be written as torque equals dl dt. So the net torque on an object or a system, a net torque on a rotating system, is equal to the time rate of change of the angular momentum. That's why if there's no net torque, right, as we talked about, then this has to be zero, which means the angular momentum does not change, it's conserved. Okay? It's only if we have a net torque, then we will change the angular momentum of a system. So if the spinning rate, if you will, or the angular momentum in a system changes, that takes a net torque. Just like to change the velocity of a linear system, we have to have a net force. Okay, we have to create acceleration, and so the only way we get angular acceleration or a changing omega value, right, because L is equal to I omega, would be to have a net torque. Okay, so this is all very consistent. Our rules for these things are very consistent, and we continue with that the change of variable, if you will. Of course, if we weren't talking about an instantaneous value, if you wanted to look at the average torque over a period of time applied to an object, and you knew, the torque, the average torque applied was a certain amount for a period of time, then that average torque is going to have to be equal to the change in the angular momentum over the change in that time. In other words, this is just the kind of the algebraic version, if you will, of the calculus version of the equation torque equals dl dt. So this can be a handy equation with some problems as well. Okay, and so the total angular momentum of a system is going to be the vector sum of all the angular momenta of all the individual particles. Okay, and so just again, like we talked about, if you have a room full of air molecules and you were to add up all the little angular momentum of all those individual air molecules, and you were to add up all those vectors, all those little angular momentum vectors, that would be equal to the angular momentum of the system at large. So in other words, if you're sitting in a room that has no net swirl of air going on in it, then that means if you add up the angular momentum of all the particles in the room, they should sum up to 0. Okay, if you have no angular momentum going on in the system at large, then summing up all the individual angular momentums should add up to the total angular momentum of the system. Okay. With time, the angular momentum of the individual particles may change. Of course, air molecules banging into each other, if they're spinning and moving and they bang into each other, they're liable to change their spin. They could change their individual angular momentums. But when you add them all up, you take each individual molecule and you add up its angular momentum, you're going to end up being equal to the original, angular momentum of the entire system. And so if that angular momentum of the system is changing, then that can be found by adding up the time rate of change of all the little angular momentum of all the individual molecules, and that's also going to be equal to the sum of all the little individual torques that are applied. In other words, the net torque acting on a system of particles is equal to the time rate of change of the system's total angular momentum. So we're basically proving, this is kind of showing you that this is all consistent. Okay, if I can add up all these individual little angular momentums to get the overall angular momentum, then if this big thing's changing, that means the little things had to change the same way. And if I, to change the angular momentum of a single little particle, air particle or air molecule, that's going to take a little bit of torque. And if I add all those up, we already talked about that we get the net torque on a system by adding up all the individual little torques. So again, everything works out. We can apply this, kind of to a big system, or to by summing up all the little angular momentums and torques in a system. If we sum them all together, we're still going to get this effect, which is the net torque on the system is equal to the time rate of change of the angular momentum of the system. And of course, this slide continues to make the point that the equations that we had before in the course directly correspond to new equations and new variables. Okay, so for angular momentum, we now have linear momentum becomes angular momentum. Okay, different ways that we wrote Newton's second law, right? That was one of the ways we said that's how Isaac Newton wrote his law. That becomes this now. So everywhere we saw a torque, we put a, everywhere we saw force, we put a torque. Everywhere we saw a momentum, we put now angular momentum, or L. And so again, our conservation law was that the linear momentum has to be constant if you don't have a net force. And now we find out that the angular momentum is constant if we don't have a net torque. So once again, this chart and the chart we had in the last lecture, I believe it was the last lecture, pretty much summarize this nice change of variable or change of units while maintaining the overall structure of the physics. Okay, so let's take a look at an example, and after I read through this, if you want to challenge yourself, you could pause the video and try to work this out before continuing. But here we have an old-fashioned vinyl record album, and it's rotating on a record player. The mass of the turntable and record together, okay, so the part that's spinning, is together they have a mass of 0.85 kilograms, and of course they're like a disc, okay, as far as modeling them. And it has a radius of 15 centimeters. So the distance from the center of the record out towards the very edge is 15 centimeters. Okay? The record rotates at 33 1/3 RPM. Okay? the record would be rotating this way in this particular case, if you're not familiar with these devices. And 33 1/3 RPM stands for revolutions per minute. So it's going to go around the record, the record's going to go around 33 1/3 times in a minute. That's what that means. And the stylus arm, which is this part, the part that sticks out here, okay, the stylus arm has been counterbalanced so that it has an overall weight of 20 grams where it rests on the record. And it rests on the record here, right up in here where the needle or the stylus is underneath that, and that's what rides in the grooves of the record to read the record information. So that's where the weight of the stylus arm would be placed, is at the position of the stylus right here, okay, or where the needle is, okay. And so it says the coefficient of friction between the stylus or the needle and the record is 0.22, and assume the record's playing with the stylus at a radius of 10 centimeters from the center. So that means that this distance out to where the needle is about 10 centimeters. And they want to know how long will the record take to stop when someone pulls the plug on the record player. If all those initial setup conditions that were given there are true, and this thing's chugging along, and now somebody pulls the plug, how long will it take the friction there to slow this record player down to a stop? Okay, so how do we go about solving this? Well, the first thing we do, of course, is make use of the information they gave us. We know that the stylus mass, the stylus has been counterweighted so that the mass that's coming down, the effective mass that's resting down on the record was 20 grams, as indicated up here in the problem. And so we take 20 grams, convert that to kilograms, and then obviously we multiply that by 9.8 meters per second squared to get our force of gravity or our weight down on the stylus. And we do that, we get our answer of about 0.196 newtons. And so that's our weight force. And of course, since there's nothing accelerating up or down off the record, since this is really a rotational question, the normal force is balancing. If you could imagine the weight force here is into the picture, right, pushing down towards the center of the earth, and then the normal force would be up, supporting that at the surface of the record. And so the normal force is going to be the same size as this weight force. Given that they told us that the coefficient of friction was 0.22, then the amount of kinetic friction we have is 0.22 times 0.196, and we get an answer for that of about 0.04312 newtons. We can then use that information, of course, for the friction to calculate the net torque, because assuming that the spindle itself is very low friction and would spin easily, then the only thing that's slowing this record player down after the plug is pulled really is the stylus rubbing on the record, or at least that's the simplicity of the question is meant to assume that. And so now we take the friction force times its moment arm. Well, again, the friction is being applied along the direction on the record. Let's see if I can get this to write properly up here. There we go. The direction of the friction, of course, is along this direction. The record's rotating this way, and so the friction is actually resisting. It's kind of pulling this direction on the stylus arm. Okay, which means that the stylus arm is pulling this way, right, towards the the other direction to slow the record down. Okay, so notice if that's the line of action of the force right there, you get a different color, line of action of the force is here, then the moment arm is the shortest distance from the, which is the perpendicular distance from the center of rotation, which is really just the radius at which that friction acts, which we were told was 10 centimeters. Right, we were told it's 10 centimeters up here where the stylus is. So basically we take the friction force of 0.04312 newtons times that moment arm of 0.10, and when we multiply those we get the amount of torque that's slowing down the record player. And again, notice it turns out positive here because again, the presumption is our record is spinning in a negative direction, and so the torque would actually be acting the other direction so as to slow the record down. We can continue along by now assuming the record and the turntable that it rests on are spinning together and that they're a disk. The rotational inertia of a disk, okay, is, as we've talked about before, is 1/2 mr squared. And so we take 1/2 times the mass of the record and disk together times the radius squared. And again, that radius, of course, has to be the entire radius of the disk, which is our entire 15 centimeters in this case, right? The 15 centimeters up here. And so when we go ahead and do that calculation, we get the moment of inertia or rotational inertia for this turntable and record that are spinning of about 0.0095625 kilogram meter squared. At this point, now we can take the original angular velocity and the fact that we know the final angular velocity, 0, okay, because the question asked here about how long does it take for the record to stop when someone pulls the plug. So our final angular velocity is going to be 0. That one's pretty straightforward. Okay. At this point, though, the original angular velocity is not in standard units; it's in RPM. But we do know there's 2 pi radians per revolution, and we do know that 60 seconds is the same as a minute. And so if this is revolutions per minute, another way we could write that would be like revs per minute, right, is what that stands for, RPM. And so we're canceling the units of revs up top with the rev on the bottom. The minutes here cancel with the minutes there, and we will end up in units of radians per second, which is our standard unit. So we go ahead and do that, and we get an answer of minus 3.49 radians per second. Again, why is it considered negative? Because, again, as viewed in this situation, the record would be rotating clockwise, which is considered a negative direction as far as mathematicians are concerned, and so that is why that's negative. Now, delta L, right, if we can figure out the change in angular momentum, we can then relate that back to the net torque and solve out for the time. So to determine the change in angular momentum, of course, can be found by taking the final angular momentum minus the original. Well, the final angular momentum is going to be pretty easy because that's just going to be 0. Right? It's not moving at the end. And the original angular momentum is going to be I original times omega original. So in other words, the I here, because the shape of the record player isn't changing, nothing's changing as far as the rotational inertia of the record and the turntable, we can factor that out and say that, well, our change in angular momentum here is the same as taking the moment of inertia or rotational inertia times the change in omega final minus omega original. And so we go ahead and do that. We say, well, here's my I value, the moment of inertia or rotational inertia for the record player and turntable together. We found it up here. That is 0.00956 in standard units. The original or the final angular velocity is 0. The original angular velocity was minus 3.49. And so when we look at the change in omega here, it's omega final minus omega original. So omega final is 0. And then we subtract off omega original, which is a negative number, and we have a negative, we're subtracting a negative, which becomes positive, and we find out that the change in angular momentum in the system here, okay, the change in angular momentum in the system, when we calculate it out, is positive, and it's about 0.03336 kilogram meters squared per second, okay? So to finish this up, we now say, all right, well, we know that our angular momentum change is this amount, 0.03336. We know our net torque from the friction is 0.004312. And then we know that the law says that, hey, if you have a net torque applied to a rotating system, that's going to be equal to, okay, the average net torque is going to be equal to the time rate of change of the angular momentum. Or in other words, dl dt is equal to the net torque, or our average torque is over the period of time is going to be delta L over delta T. So we know delta L, we know delta T, we simply have to do a division here, and we should end up solving out for the time. So rearranging this equation, solving for delta T, right? Delta T is going to be equal to delta L over the net torque. And so taking the delta L value here and dividing by the net torque, we find out that it's going to take 7.74 seconds for this turntable to stop turning after someone pulls the plug. Now, if that is correct, it would be nice to be able to confirm that somehow, and fortunately there's a way to do that. Here we see that we can check our answer. We can check our answer. All right. We've got our torque. We've got our rotational inertia. And we know another law, torque net equals IA. Okay. Torque equals IA. That's basically Newton's second law written for a system that does not change rotational inertia, which is what we have here. So if I go ahead and use that, I can solve for alpha, the angular acceleration, by taking the torque divided by the rotational inertia, or moment of inertia. When I do that, I get my answer for alpha of 0.451 radians per second squared. That's the angular acceleration. Notice that it's positive. It's positive, but our angular velocity initially is negative, right? Because it's rotating clockwise. So that means that the angular acceleration has a sign that's opposite the original angular velocity. And of course, when you have acceleration and velocity opposite, that means things are going to slow down, which is what we expect. So now we go to our kinematic equations for rotational motion, or rotational kinematics, or angular kinematics. And we know that omega final equals omega original plus alpha t. We know omega final 0. We know omega original was minus 3.49 radians per second. We found that our angular acceleration here is positive 0.451. That allows us to set up an equation that has only the unknown t. We solve that out for t, and we find out, ta-da, we get the same answer of about 7.74 seconds. So that's a nice way to check our answer. Now, the last thing to talk about today, to wrap this up, beyond practicing problems, we'll probably look at some problems some more on Wednesday. For Wednesday's class, we'll start to look at some more problems related to all this, and I'll get your next homework set up online. But the gyroscope is an interesting thing. If you've never seen a gyroscope, they were a common little toy that in years gone by that kids would play with and so forth. I encourage you, if you don't know what a gyroscope is, as modern day people, I honestly, for my generation, everybody would know what a gyroscope is, but again, I'm not sure how many of you have seen gyroscopes. Maybe it's still a common thing, maybe it isn't, I don't know. But you should definitely look up and explore and learn what a gyroscope is. Okay, and basically we're going to look at a gyroscope here, which is in a minute, which is just a spinning bicycle wheel. And it turns out if this is the bicycle wheel as shown here, it's going to be spinning as it shows in a counterclockwise direction. And so that's considered a positive angular velocity. So our omega vector, even though they show the direction it's spinning, remember that in this three-dimensional diagram, the angular velocity vector really would point out here. Let me get a little darker color here, perhaps, to sketch that. Our angular velocity follows a right-hand rule, and so our omega vector is pointing out this way, which is as well the same direction as our L. So both L and omega point along the positive x-axis here as shown. They do kind of show L back in here, if you can see it. They do draw that L vector pointing in the positive x direction. The direction from the center of rotation, if this is a rotating stand where something's going to pivot about, as they show here, if this rotating stand, the distance from the origin here out to where our force is applied, and what's our force? It's going to be the weight of the bicycle wheel, mg. The weight of the bicycle wheel is going to be trying to pull it down. That r vector, of course, points in the same general direction as L along the positive x-axis. So if you remember, we get our torque by taking r cross F. And so as we do r crossed into F, we would have kind of the r coming out this way, the F coming down this way. And as I use my right-hand rule crossing r into F, okay, if you can visualize that three-dimensionally, I end up getting a torque that's going to point this way. Okay, it's going to point as shown in kind of the positive y direction there. Okay, so r crossed into F, and this is our F down here, our mg, right? R crossed into F gives me a torque as shown kind of to the right. And so what this would do, okay, what the torque would do is change the angular momentum vector. Well, how's it going to change it? it's going to cause the angular momentum vector as time goes to kind of start to move this direction, right? So it's hard for me to draw this in here. I'm trying my best I can to explain this, but the L vector is going to start to want to come to the right, if you will, the direction that the torque's pulling it. All right, that's the direction the momentum vector has to change. And so as L, initially points this way, then it's going to start to point this way and this way, and my torque keeps pointing around like this and just keeps causing the L vector, the L initial, and then the L, it's just going to keep going around. And this causes what we call precession. So if I spin this bicycle wheel fast enough, okay, and I put it on some kind of little arm, I put it on an arm with a support, and I can support it right here, it's going to precess, which means that the wheel is going to, as it's spinning, it's also going to move around this support circle and precess. But another interesting thing happens, and that is because the delta L vector can only change the direction of the net torque, delta L does not really change down. The wheel's not going to fall unless delta L changes magnitude, because our torque is perpendicular, and it's going to cause the L vector, the angular momentum vector, to stay in this plane and go around. As L loses magnitude, now we can start to have this wheel start to sag. But initially, when you first see this, if you've never seen this, it's quite baffling. It's actually the demonstration that made me a physics major. Once I saw this demonstration up at University Park, it was Dr. Pratt back in those days, did it in Physics 211. It was Physics 201 back in those days. He did this demonstration, and that was the moment I decided I was going to become a physics major, because I thought this was so cool. So let's take a look at a person actually spinning a bicycle wheel and watching how this works. Okay, here's we see the gentleman. He's going to show you that if he tried to support this bicycle wheel about the end of its support handle, it would just fall over. Gravity would just pull the wheel down. But if he ties a string onto the end of the handle and gets the wheel spinning very quickly and releases it, you'll notice that it appears to defy gravity. It looks as if it looks odd. We expect the bicycle wheel to fall from gravity, but the torque vector is causing the angular momentum vector to precess around in a horizontal circle. It does not pull downward because of this law of conservation of angular momentum. Okay, this torque vector that's being applied by gravity, trying to pull it down, does not pull it down, but causes it to precess horizontally. And so it creates almost a magical effect, almost looks like anti-gravity, or somehow it's defying gravity. And again, it's a very exciting thing to see. If we were live in the classroom, I would love to do it for you. But of course, we're in this situation. But I hope the demo there, the picture of that, it helps to at least get you excited about how that works. Okay, so anyway, continue to work hard, and we'll get into some more problem solving and so forth in our next class, and just continue to work hard. Make sure you don't let up. Okay, we're coming down the home stretch, and contact me with any questions you have or any issues. Thank you. Have a great day.